In this video, we're going to be exploring scientific notation. Let's start by looking at some really big numbers that someone involved in science might actually be looking at. Like the distance from the Earth to the Moon is 238,900 miles. The closest that Earth is to Mars is 33,900,000 miles. Earth to Venus at its closest, 26 million miles. The distance from Earth to the Sun, 91,400,000 miles. These are really big numbers. You notice a lot of zeros there, and, well, let's be honest, do you really want to have to write down these huge numbers every single time you're going to do some operations? Well, scientists would say no. We have a much quicker way of writing these down using scientific notation. And before we get into that, let's explore the number 10. This is going to be very useful to us because it is crucial to scientific notation. First, let's look at 10 to the first power. Anything to the first power is itself, that's 10. How about 10 to the second power? That's going to be 10 times 10, or 100. And then we have 10 to the third power. That's 10 times 10 times 10, which is going to be 1,000. Have you noticed a pattern yet? Take a look at the zeros. Here we have 1 0, and it's being raised to the first power. Here we have 2 zeros being raised to the second power. Here we have 3 zeros raised to the third power. Raising 10 to various exponents is very, very simple. All you need to do is count the zeros. So how many zeros are going to be after the 1 when I do 10 to the sixth power? 6 zeros. 2, 3, 4, 5, 6. I'll put some commas in there so we can see what we're dealing with. 10 to the sixth power is 1 million. Real simple, right? So anytime we multiply by 10, that's still what we're doing, is counting zeros. 3 times 10 is 30. 3 times 100 is 300. And 3 times 10,000 is 30,000. Okay? That's the first important part of doing scientific notation. Now here's our definition. It's a way of expressing very large and very small numbers as a product greater than or equal to 1 and less than 10 times 10 to some power. So here is our number n that is being multiplied by the number 10 to some power p. So let's look at those really big numbers that we were looking at earlier, like the distance from the Earth to the Moon. In scientific notation, we want to turn this into something that's between 1 and 10. Well, there is, in fact, let me write this out again, but a little bit bigger so that I can work with it, and I'm going to take out the comma. There's really a decimal point here, isn't there? We're saying 238,900.0, essentially. So in order to do this, we need to move that decimal 1, 2, 3, 4, 5 places in that direction, because the number 2.389 meets our first criteria of being a number that is greater than or equal to 1 and is less than 10. If we did 23.89, well, that's bigger than 10. That's too big. Times 10 to the, well, how many places are we going to need to move this decimal back the other way if we want to turn it into what we did here. How many jumps or hops did we have? We had 5 of them. And there you go. The distance from the Earth to the Moon in scientific notation is 2.389 times 10 to the 5th power miles. Earth to Mars. Well, let's take a look. How many hops do we need to do? 1, 2, 3, 4, 5, 6, 7 hops. We're looking at 3.39 times 10 to the 7th power. To Venus. 1, 2, 3, 4, 5, 6, 7 hops again. 2.6 times 10 to the 7th power miles. And then the last one, the Earth to the Sun. 1, 2, 3, 4, 5, 6, 7 hops again. 9.14 times 10 to the 7th power miles. And there we go. Definitely working with a lot smaller numbers this time, rather than actually having to write out 91,400,000. So in my definition, I did say that it's used not only to represent very large numbers, but scientific notation is also used for very small numbers. So let's go back to looking at just the number 10 again, to negative exponents. Okay, 10 to the negative 1st power is 1/10, or we could say 0.1 or 0.1. 10 to the negative 2nd power is 1 over 100, which is going to be 0.01, or as a placeholder, a lot of people like to do 0.01. And we're going to go ahead and do it that way, because just like moving the decimal point to the right, if you're going to go from scientific notation into the regular numbers, we're going to be moving it to the left with these numbers. For instance, here, 28.2 times 0.01, or 1/10, moves the decimal point one place to the left. So we have 2.82. And here, the same number, 28.2 multiplied by 0.01, is going to move the decimal 2 places to the left. So we can say 0.282, or what some people like to write is 0.282. Did you notice something that we can still do just like we did when we raised 10 to the positive numbers? As long as we do include this place holding 0, all we need to do is count the zeros. And that tells us how many hops there are. Of course, this number here also tells us how many hops there are. So let's do some. Small numbers. We have 0.016. The number that this can become with 2 hops to the right is 1.6 times 10 to the, how many hops were there? There were 2 hops. But is the real number bigger than 1.6 or smaller than 1.6? It's smaller. So we'll continue with those negatives. It's 1.6 times 10 to the negative 2nd power. And we have another example here. We need to get it to be between 1 and 10. So we're going to do 1, 2, 3, 4 hops. That's 3.58 times 10 to the negative 4th. There were 4 hops. and it is smaller. And notice how the number of zeros is the same as our exponent. Because we included the place holding 0 in front of the decimal, we have 2 of them, our exponent's a -2. We had 4 zeros, the exponent is -4. It's going to be a really useful observation as we move into this next slide, because we've done several where we converted from just standard notation into scientific notation. But what about going back the other way? That is something we need to do. I just have 2 examples here. It's going to be 5.27 times 10 to the third. And the one below is 10 to the -3rd. How many hops is that going to be? It's going to be 3 hops in both cases. In this first one, it's going to be 3 hops to the right. 1, 2, 3. So it becomes 5, 2, 7, and then there's another item here. So it's 5,270. And then going back the other way, we're going to do 3 hops in the other direction. 1, 2, 3. Notice I've got 2 empty loops here. So that's going to become 0.00527. But if you go ahead and include the place holding 0, you'll notice that it's still useful to just notate that there's 3 zeros and it's being raised to the -3rd power. So that's a way you can do it without having to worry about the number of hops. But that is our lesson on what is scientific notation.